Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Lecture 102, electric potential. Last time we talked about the electrical potential energy. This time we're going to talk about the electric potential. So let me start by writing the following expression. I want to consider a small change in the potential energy. Okay, and I'm going to be acting against a field. So I'm going to put a test charge, positive test charge, in a positive electric field somewhere, and I'm going to push against the field. So the force that I'm applying will be in the force that I'm working against is in the opposite direction that I'm pushing, okay? So I'll write this as minus Q naught times E dot dl. That's the path that I'm taking. We can assume I'm taking a straight path if you want, so that's just going to be E times the distance that I move, right? This is just work, right? The negative sign, though, I'm putting in there. That way I make sure that in a positive field, a positive test charge, will go from high potential to low potential if I just let it go, if I let it accelerate, okay? That's what the negative charge means. That means that if I put a negative charge in there, right, it will naturally accelerate in a direction that takes it from a low potential to a high potential, okay? That's because it's attractive. But that's what the sign convention is all about. All right, now you remember that the electric field itself is a funny function, right, or funny thing. It is the force per unit charge. So we take the force and we divide it by the test charge, right? And that is our electric field. Similarly, I'm going to take this little bit of work or potential energy and divide it by Q naught. And I'm going to call this the electric potential, or a small change in the electric potential, which will be equal to du over Q naught. So it's the work per charge, the change in potential energy per charge, and it's going to be equal to minus E dot dl. So let me just draw a little illustration here. Here I've got some electric field. These are my electric field lines. Put in a charge. It's a positive charge in this field. We'll call it Q naught if you want. And the force that's acting upon it is tangential to the field line here, yes? Yeah. But of course, I'm pushing it against that. That's the work that I'm doing, okay? Because I'm taking it from a low potential to a higher potential as I push it, right? Yeah. So that's what we were set up here to do. But let's look at the change. If we move from some start position to a finish position, there'll be a change in this potential, right? Which is, again, it's the work per charge, or the change in potential energy per charge. And the charge that I'm thinking of is this test charge that I put in to evaluate the field. So this delta V is just V final minus V initial. And it's going to be equal to minus the integral from initial to final of E dot dl. Let me just comment for a second on the units here. So you might recall that the electric field had units, newtons per Coulomb, right? Because it was the force, right? The Coulomb force divided by the charge of the test charge that we put there at that point to see what the force is, yes? So it has units of newtons per Coulomb. Similarly, our voltage, our electric potential, has units of joules per Coulomb because it's some amount of potential energy per charge, right? Yeah. So it'll have joules per Coulomb. But we're going to redefine this as volts. So 1 joule per Coulomb we'll call 1 volt. There. And unfortunately, the volt symbol is the same as the symbol V I've used for potential, but that's okay. And you've heard of volts before, right? With batteries, like a 9-volt battery. Right now you know what the volt thing is, okay? It's a measure of the electric potential. Now, as a homework assignment, you will be challenged with demonstrating that the electric field can also be written in different units than newtons per Coulomb. It can be written in units of volts per meter. Okay? And that, you can do a little unit analysis and you'll be able to show that. But this is a useful way this is a useful unit for the electric field, as you'll soon see. Okay? I want to consider a slightly different electric field. This one obviously has some variation, as you can see. What if we made a really easy electric field, though? Let's let the electric field be equal to some constant value in the x direction only. Okay, so it's a uniform electric field. Doesn't change with distance, okay? Just a uniform electric field in the x direction. So we can then write that delta V is equal to some, I'm going to just write it x naught, x1, something like that, of E dot dl is just going to become E naught times x hat dot dl, right? And so you can see that as we take the dot product of this unit vector with dl, right, this is just going to reduce, and I needed the minus sign, it's just going to reduce to the following, x naught to x1 of E naught, well, we actually could pull the E naught out because it's not going to affect the integral any. E naught times x dot dl is just going to become dx, right? We're only going to accrue any change in the direction of the path length that's in the x direction, right? And this is an easy integral to do, right? This is just E minus E naught times delta x, where delta x is x1 minus x naught, okay? So what does that say? And that's saying that delta V is going to decrease, that's the negative sign, right, by the amount E naught times delta x. So if I just take a charge and I clamp it in some position and then let it go in this uniform electric field, it's going to accelerate. And the change in position, the displacement, right, will decrease the potential, the electric potential, by an amount minus E naught times the distance that I move, okay? And so remembering that delta V, right, the change in potential is delta U divided by Q naught, I can easily come up with an expression for delta U, which is going to be equal to minus Q naught E naught delta x. So that's the potential energy, the change in the potential energy. So this change here will be in volts, this change here will be in joules, okay? And let us recall the work energy theorem. Do you remember the work energy theorem? I'll put in the video which lecture the work energy theorem is in. I just don't remember what it is off the top of my head. The work energy theorem says that in a conservative field, anyways, or for conservative forces, the change in potential energy is equal to the change in the kinetic energy, right? So if I decrease the potential energy, I must increase the kinetic energy because the sum of the two is conserved, right? This is the work energy theorem. This is why we like to use electric potential, okay? Because it would be very difficult for me to calculate the motion of a charge, even in a uniform field. It might not be so bad in a uniform field, but in a more complicated field, it would be difficult, okay? Yeah. But sometimes, remember the racetrack problems, right? We get the funny racetrack that's shaped, you know, kind of like this, and I ask, you know, about, I need to go a little higher, about the motion of the little ball that I release as it rolls down the hill, right? And I might ask a question like, how fast is it going when it reaches the top of this hill here? And you're like, well, that's a pretty hard question to answer because you need to like calculate the force that's accrued in this kind of complicated shape that I'm going through here, right? That could be a tricky problem to solve using Newtonian mechanics, but as it turns out, the work energy theorem saves us because it says, well, if I know what the change in potential energy is between here and here, which I do, it's just mgh, right? And if my initial velocity was 0, I can easily calculate what the final velocity is here at the top of this peak because that's the change in potential energy that we had, right? And so we just simply say, you know, the kinetic energy, 1/2 mass times velocity squared, is equal to mgh, and we can solve for what the velocity of the car or ball will be at this hill, okay? And that's a really useful thing because you don't have to do all the complicated calculations for the equations of motion for the car as it accelerates and decelerates going on this bumpy ride. And we can do the same thing with charge, so let's do that here. We put this charge in a uniform electric field, we let it go. We'll use the work energy theorem, right? So it says that this delta U, right, I'll write work energy theorem. It says that delta U is equal to delta T. Delta T is, I'll write it as KE because sometimes people get confused about that. Change in kinetic energy. And I could, if I wanted to, I could write delta PE for potential energy equals delta KE, change in kinetic energy, right? So all I have to do is just say, all right, well, 1/2 mass times the velocity squared, this is the change in the kinetic energy. If I said that at my x naught position, if I started out with 0 velocity, it's not moving, right? We can just solve for V. Well, we set this equal to the change in the potential energy, which is just minus Q naught E naught delta x. But I'm going to absorb the minus sign into the delta x because if I'm letting it do the work such that I'm going from high potential to low potential, then the delta x is going to be negative, okay? So now I'll solve for the velocity. The velocity will be equal to the square root of 2 times q naught times E naught times delta x divided by the mass. Okay? Let's do a real example. Let's say that E naught, I'm going to need a little more room. So let me put my result up here. I don't need to show this work. I'm just going to say that V is equal to square root of 2 q naught E naught delta x over the mass. Let's let E naught be equal to 10,000, it's 10 to the 5, newtons per Coulomb. Okay? And the mass of the electron, by the way, is equal to 9.1 times 10 to the minus 31 kilograms, I believe. So let's put these down. And the charge of the electron, QE, is equal to 1.6, just 1.6? Yeah. Times 10 to the 19th, minus 19th coulombs. Okay, so I'm going to use this information in this velocity formula. So the velocity here is equal to 2 times 1.6. And there's a minus sign here. Maybe I should have left the minus sign in before, right? Times 10 to the minus 19 coulombs, because this is an electron after all, right? So it's going to go in the opposite direction, which means our delta x is positive. But if I hadn't absorbed that minus sign into the delta x, then it would cancel with the negative sign from the charge of the electron, right? That's a detail. Don't worry about that too much. So we've got 1.6 times 10 to the minus 19 coulombs times 2. The electric field is times 10 to the 5th newtons per Coulomb. And we need a delta x. Let's let this accelerate over a distance of 1 meter. Okay, so I'll let delta x be equal to 1 meter. So that's times 1 meter. And we're going to divide that by 9.1 times 10 to the minus 31 kilograms. Okay, you can see the coulombs and the coulombs cancel out here. And we're going to get that the velocity is equal to square root of, well, 2 times 1.6, that's 3.2, over 9.1, that's a tough one, 3.2 over 9.1. Let's just do with the powers of 10, right, times 10 to the minus 19. We'll write it like this, 10 to the minus 19 plus 31 plus 5. So that's plus 36 Newton meters per kilogram. 17 Newton meters per kilogram. Remember, the joule is a Newton meter, right? So let's work on the units here. So a Newton times a meter is equal to a kilogram times a meter squared per second squared. So plugging that in here, we get that over kg. So this means that the units that we have in here now are meters squared per second squared. Okay? It's just the units. And so what is this actually equal to? Let's see. Who has a calculator? Thank you. All right, so we have the 3.2 divided by 9.1 part gives me 0.352, we'll call it. So 0.352. And then times 10 to the 17, we need to take the answer, raise it to the, no, not raise it to the, have to figure out how to use your calculator. So I get, when I take the square root of all of this, I get 187, and I'm just going to round it all off here, and that'll be meters per second because this was meters squared per second squared. 187, all right, 1875, so we could call it 188, I suppose, also. But, you know, this is a very fast speed, right? So if I divide it by the speed of light, which is roughly 2.99 times 10 to the 8th meters per second squared, or meters per second, excuse me, I should get this in terms of c, right? So I can do that. If I take this and I divide the answer by 2.99, I get 0.63. So this is also equal to 0.63 times the speed of light. So it's 63% the speed of light. It's pretty fast, huh? Yeah, after just 1 meter of acceleration. So kind of ugly here with the units, but that's why the volts are nice. Let me just show you how to do that now, okay? So if I, instead of using 10 to the 5 newtons per Coulomb, I think of it as 10 to the 5 volts per meter, right? And instead of thinking of the mass of the electron is 9.1 times 10 to the minus 31 kilograms, I think of it as 0.511 times 10 to the 6 electron volts per c squared. And you're thinking, what the heck is that electron volt thing? Well, one electron volt is equal to 1.6, probably 602, but it's fine, times 10 to the minus 19 joules. So it's a really nice unit. This is the unit you would get if you took the charge of a single electron, right, and multiplied it times 1 volt. Okay? Excuse me. Yeah, times 1 volt. So if you took that many coulombs times 1 volt, I would get 1.6 times 10 to the minus 19 joules, which is what we call 1 electron volt. Okay? So I can write the speed of the mass of things in terms of electron volts per c squared. Why per c squared? Because E equals mc squared, right? We just solved for m. So m is equal to E over c squared. So we're writing masses in a kind of a relativistic way. We're writing it as energy per c squared. Okay?
All right.
So 0.511 times 10 to the 6 electron volts per c squared. In this case, we no longer need, the charge of the electron. We just need to write that the velocity is going to be equal to the square root. We take these 10 to the 5 volts per meter times 1 meter. That gives me 10 to the 5. We'll have 10 to the 5 electron volts. And we divide that by the mass of the electron, which is 0.511 electron volts per c squared. And when I run the numbers on this, I'll get 0.39 times 10. No, I don't need that. I just get 0.39 times c, and if I take the square root of this, I get 0.63 c. So we get our speeds in terms of multiples of the speed of light out quite naturally this way. Okay? So it's a kind of a handy way to work, to use these alternative units, including the electron volt. Okay? Because it works quite naturally for small particles like electrons and protons and stuff like that being accelerated in fields. The last thing I want to do is, I'm going to erase. Last thing I want to do is talk about how, I want to derive the formula, or show you the formula that you'll usually find in textbooks regarding the potential of a system of charges, right? So if you had a system, a finite number of charges, and you want to put them in place, right? This is how you come up with the equation for that. So, but we're going to think of it in terms of potential this time. Electric potential. This will be charge 1, and then I'll put charge 2 over here. I like to use the curly Q's. And maybe charge 3 over here. And we'll specify the distance between these as just call it R12, and we'll call this R13. We'll call this R23. Okay? And if we start with charge 1, then the work, right, that we do to put this charge in is still 0, because there's no charges there yet, right? So we get 0. Plus the work, now we're going to move charge 2 in, right? And the work to move charge 2 in is just going to be Q2 times the voltage, or the potential, times the potential of, we'll call it 2, 1. Okay? That's the electric potential between 2, 1. So if I multiply the electric potential times charge, remember the electric potential is just, it's the potential energy per charge. So when I multiply it times the charge, that tells me the work, you see? By definition. And now I'm going to move in charge 3, right? And I'm going to write this as work 1, 2, 3. This is the ordering. I move in charge 1 first, then charge 2, and finally charge 3. And so the work for charge 3, I'll just add that in. That's going to be Q3 times, well, we're going to have the potential between, the potential, we'll call it V23, or maybe V32, plus V31. Okay? But now let me do it the other way around. Let me do the order 3, 2, 1. W3, 2, 1. This time I bring in charge 3 first, right? So that'll be 0. Then I'll bring in charge 2. So that'll be Q2, but I already have charge 3 here, so it'll be the potential difference between 2 and 3. So this will be V32. I'll write it like that. And then I finally bring in charge 1. That's Q1 times, we'll have the potential difference between 2, 1 plus the potential difference between 3, 1. Okay? I just did it both ways, right? And you might remember that there is no difference in the work when you bring charges in one at a time. The order doesn't matter, right? Yeah. But I want to add these two together, okay? If I add these two together, then I can say that the work is equal to 1/2 1, 2, 3 plus work 3, 2, 1. Because I'm overcounting by a factor of 2, so I have to take half of it. But why did I do it, right? And I did it because I can rearrange things in a convenient way. I'll start with this. I'll have Q1 times V21 plus V31. And actually, I may just change the ordering of this. I'm going to write this as 1, 2, and 1, 3. Okay? That way, the charge number here corresponds to the first subscript on the potential that I've written. That's just the potential difference between, so V12 is the potential difference between this point and this point. Okay? Now I'm going to put plus Q2. Here's Q2. I've got two terms from that. I've got V23 and V21. So V21 plus V23. And then finally, plus Q3, which is up here, Q3 times V31 plus V32. And I can write this as 1/2 times the sum of I equals 1 to n, where n is the number of charges, okay? Times Qi, and I'm going to write Vi, okay? And what does Vi mean? Where Vi is equal to, it's the sum, I not equal to j, okay? Of Vij. Okay, that's what it means. So when I look at this, I say, what are the possible values of it, right? If I let, let's let I equal 2, for example. I equals 2, that means we have Q2 times V21 plus V, can't do 2, 2, because that would make I equal to j, so we skip that one, and we do V23. And we go all the way up to n, you see? And I guess we could write up to n, something like that. Okay? So it's just an alternative way of writing this, and this is how you'll usually see it in books. So I wanted you to have that formula at your disposal and to practice using it a little bit, that way you understand it. And so that is the way to look at the work required to assemble these charges using potential or potential energy differences. Okay? And I'll give you some homework problems where you get to see, right, what these potential energy differences, what these potential differences mean, and how it affects the solution of the problem. But you'll recall from last time we talked about equipotential surfaces, right? These regions where the potential energy doesn't change, which means you can move through there freely without having to do work, right? Yeah. And so same thing applies for the electric potential. The electric potential does not change on an equipotential surface, okay? And so you can think of things like conductors where charges are free to move, right? If I bring a conductor into contact with something that has at a certain potential, electric potential, then that entire conductor will now become at that electric potential as well. Okay? And this will become more relevant when we start talking about circuits and stuff, electrical circuits, okay? I think that's all I wanted to cover. Oh, wait, one more thing I wanted to add here. As a consequence of this, though, right, you can also write out for continuous distributions something to the effect of u is equal to 1/2 the integral of lambda times v times dr. Could also be 1/2 the integral of sigma times the potential times some dA. That's for areas, for charge density in terms of area, right? But also in terms of volume. So the integral of rho times the voltage or potential times dV, where V is the volume. I'll write it like that. Okay? So there are those variations of it as well. We're not going to do any problems of that nature, I think. So, but I'll just put it out there that you can, of course, use this formula for continuous charge distributions as well. But I'm not going to put any in the homework. So, I think that's it.